Here's a somewhat more challenging rigid body kinetics problem in 2D, which looks at a uniform slender rod which is supported on a wheel, and then that wheel is constrained to this oblique channel basically. And what we know is that the rod is initially released from rest, and we're asked to find the initial acceleration of this point here that we call A, which is on the actual wheel that's traveling along the channel basically. So this is the kind of question that you would see if you're doing some kind of engineering degree. Maybe if you're a first or a second year student, you could do something, you could expect to see something like this in your mechanics module. And if you have any similar things that you'd like to see on the channel, let me know in the comments. So as usual with those kinds of questions, what I would do is, first of all, the most important thing is to draw a free body diagram, right? So let's draw a free body diagram. And by that I mean I'm gonna redraw the rod. I'm gonna ignore the wheel for now, just to make the diagram a bit simpler, something like that. And then I'm gonna draw the forces which are acting on the rod, right? So we know that the mass of the rod is m, we're given the length as L, and we also know that this point here is labeled as A. So which forces are acting on the rod? Well, obviously we have the weight. So we have the weight acting at the halfway point, and it's acting downwards. So that's your mg. And then we also have a normal reaction force, right? Now we neglect friction, which means there's no tangential force going this way or that way or anything like that. So the only force which is acting on point A is going to be something like this, right? So the orientation of this force is perpendicular to the channel, right? So this is kind of like a net force between the two walls of the channel and the wheel itself. And I'm just gonna say here that the direction of this normal force is in this particular way that I drew here, okay? Right, so those are all the forces. We just have two forces, and based on that we have to find the acceleration of point A. So normally what you would do at this point is you would write that the sum of forces, or the net force, right, is equal to the mass times the acceleration of the center of mass. So that's one thing, which again, this is going to give you two different equations for the acceleration, one for x, one for y. And you'd also have that the sum of moments about some point, let's call that point P, is going to be equal to the position vector of the center of mass and then cross with mass times the acceleration of the center of mass plus the moment of inertia above the center of mass times the angular acceleration. So that's all nice and well. The only issue that we have is we should pick, first of all, which point do we take moments about for rotation, and also what orientation is our coordinate system in. Because normally we would take, coordinate system like this. That's standard, and you can do this for this problem, and you will get the right answer. But if you can choose any orientation of the coordinate system, it's better to choose one which makes your life a bit easier. And in this case, my claim is that I want to have a coordinate system which I place in the center of mass, and I want my x to be this way, and I want my y to be this way. So x is going to be along the channel and y is going to be perpendicular to the channel, right? And the reason for that is because, again, you can do any orientation you want, but essentially the acceleration of point A is purely going to be in the x direction if I write it like this, which later on, as you'll see, will make calculations slightly easier. But for now, let's deal with this. So let's look at the forces in the x direction first. So in the x direction, in this x direction, not in the horizontal direction, we only have one force which is acting, and that is the x component of mg, right? So here's what we have. This angle is theta, which means this angle here is also theta, which means that this angle here is also theta. So the x component of mg will be minus mg sine theta. Right, so it's minus mg because it's acting in the negative x direction, and then this is going to equal the mass of the rod times the acceleration of the center of mass in the x direction. And we do the same thing for y. So for y we have that n, which is in the y direction, and then minus mg cos theta. Right, so mg cos theta is basically this here. That is equal to m times the acceleration of the center of mass in the y direction. So those are the two equations of motion for the acceleration of the center of mass. So let me write them again on the next page, but I'm going to simplify this a bit. So I'm going to say that minus g sine theta is equal to the acceleration of the center of mass in x, and n minus mg cos theta is going to be equal to the acceleration of center of mass in y, times m, of course. So it should be m times the acceleration of the center of mass in y. Right, so now let's do the rotation part. So for rotation, we're going to take moments above the center of mass. So we have the moments above the center of mass are going to be equal to, well, this term just vanishes because above the center of mass there's no position vector of the center of mass, right? So that's 0. So the moment above the center of mass is just the moment of inertia above the center of mass times the angular acceleration, like this. So what we do have is that above the center of mass there's only one force which is producing moment, and that force is this n here. Okay, so we have that this force n is producing a clockwise moment, so we have minus n multiplied with, so I've got L over 2 sine theta, right? So I'm leaving the vector notation alone, and I'm just doing this in the simple way. So I'm saying that n produces a clockwise moment, which means that's going to be considered negative, so it will be minus n times half L sine theta is equal to the moment of inertia above the center of mass, which is 1 over 12 ml squared times alpha. So we can cancel a couple of things. We can cancel the L's, we can cancel this 2 with this 2, and we have 6. So we're going to end up with minus n sine theta equals 1 over 6 m times L times alpha. Right, so we've got one equation. We've got, this is the second equation, and this is the third equation. And it still seems like we're missing something, because if you think about it, here we have 3 equations with 4 unknowns, right? So the unknowns are n, the normal force, the 2 components for the acceleration of the center of mass. So both of those are unknowns, and also alpha, the angular acceleration. So we need one more thing to create like a closed system, and then be able to solve for everything. So that fourth equation will actually come from a kinematic constraint. So to understand what we have to do, let's write the acceleration of point A with respect to the acceleration of the center of mass. So we have the acceleration of A is equal to the acceleration of the center of mass plus alpha cross, and then we have OA, and then minus omega squared OA. So that's Euler's equation for the acceleration of point A, which is here, with respect to point O, which is here. That's the center of mass. So let's write this out and let's see what we get. First of all, this term is equal to 0. Why is it equal to 0? Well, that's because the rod is released from rest. So at first, in the first instance, there's no velocity anywhere. Right? So this is stationary, and then it's released, and the moment it's released, we have to find what the accelerations are. So that makes life easier. Now, we know the acceleration of A will be along the channel, right? Because point A is on the wheel, and the wheel can only move along the channel, and the channel is in our x direction. So this is why we picked the x direction like this, because now we can say that the acceleration of A is purely in the x direction. So it only has this I unit vector component in it, and the j component or the y component is 0, like that. Right, so this is equal to the acceleration of the center of mass, which we don't really know much about. So that's the acceleration of the center of mass in x times I plus the acceleration of the center of mass in y times j. Okay, and then plus, and then we have our determinant I, j, k. We have our unknown angular acceleration alpha, which has 0, 0 alpha components. And then we have OA, which actually has two components because it is purely vertical, that's true, but our coordinate system looks like this, right? So that's our x and our y. So let's find the coordinates of point A with respect to the origin. So the x component should be essentially this, which is half L and then sine of theta. So it's half L sine of theta, but of course it's negative because this point A, is behind point O if you measure in this coordinate system, right? So it's behind this yellow line technically, and it's also below this other yellow line, so it's below the x-axis, which means the y coordinate is also going to be negative. So the y component is going to be minus L over 2 cosine of theta, right? Which is, of course, this part here, or I should say this part. Right, so that's what we have. Now, we're going to rewrite this on the next page, and then we're going to solve the determinant, and then we're going to compare the various components of all the vectors. So we have only this on the left, and on the right we have the acceleration of the center of mass in x times I plus the acceleration of center of mass in y times j, and then we have plus I multiplied with. So let's do the I component first. So this is gonna be 0 minus minus, so it's gonna be alpha L over 2 cosine of theta, and then plus, or I should say minus j, I guess, minus j times, and then we have again 0 and then minus minus that, so it's going to be alpha L over 2 sine theta. So alpha L over 2 sine theta. And that's it. So on the left hand side, there's no j component, which means that this 0 here has to be equal to this and this. So we can say that 0 is equal to the y component of ACM minus alpha L over 2 sine theta. So from here we get that the acceleration of the center of mass in y is equal to alpha L over 2 sine theta. And this is our fourth equation that we need to solve for pretty much everything, right? So we can now actually write all the equations that we have and start solving. So we have minus g sine theta is equal to the acceleration of the center of mass in x. Then we have n minus mg cos theta, that's equal to m times the acceleration of center of mass in y. And then we have the rotation part of the problem, so we have minus n sine theta equals 1 over 6 ml alpha over 6 ml alpha. So those were our initial three equations, and then we have this one which says that the acceleration of the center of mass in y is equal to alpha L over, make sure we copy everything right, L over 2 sine theta. And that's it. So those are four equations, four unknowns, and we can try solving for pretty much everything. So the good news is that the acceleration of the center of mass in x, we kind of know what it is. It's just minus g sine theta. So we're going to try and find what is the acceleration of the center of mass in y. And once we know this, and of course we know this, we can go back here and finally find what the acceleration of a is. And that's going to be the final answer. So let's solve essentially those three equations. And to do that, I think I first want to eliminate alpha. So if I go here, I'm going to say that alpha is going to be equal to 2 times the acceleration of the center of mass in y divided by L sine theta. And then I take this, I put in the second equation, so we have minus n sine theta is equal to 1 over 6 m L, and then instead of alpha I just write that. So 2 ACM y over L sine theta, right? And then we can cancel out the L's, we can cancel out the 2 with the 6, and we get a 3. So what we end up with is that n, right, is going to be equal to minus, so let's make sure we have everything. We have minus a third, and then we have m times the acceleration in y over sine squared of theta. So, right, we moved the sine theta in the denominator, and that's what n becomes. Just minus, and of course we move the minus to the other side, and that's what we have. And now that we have this as well, we're going to put it in this equation, and that should give us a closed form of the acceleration of the center of mass in the y direction. Okay, so let's write what n is. So n is this, so that would be minus 1 over 3 m times the acceleration of the center of mass in y over sine squared of theta, and then minus mg cos theta, so minus mg cosine of theta, and that is equal to m times the acceleration of the center of mass in y. And I think that's all we need to find this. So this is now one equation with one unknown. So to do this, I would just take this, bring it to this side, and I would have the following. So if I factorize m times the acceleration, then we get 1 plus 1 over 3 sine squared of theta. And this is going to be equal to mg, or minus mg cos theta rather. Right, now the m's cancel out, which means that we can also amplify this fraction and get one common denominator. So the acceleration of the center of mass will be minus, and then we have g cosine of theta multiplied by 3 sine squared of theta over 1 plus 3 sine squared of theta. Okay, so this is the acceleration of the center of mass in y. And that's, well, from this point onwards, we just have one more step to go to find what the question is asking us to in the first place, which is the acceleration of a. And to get the acceleration of a, we go back to our Euler's equation for acceleration. And what we previously did when we got the equation that we labeled 4 was we looked at the y components only, right? So the y components of those vectors gave us the fourth equation that we needed, and the x component, as you'll see, will give us the answer that we're looking for. So if we extract the x components, we have that the x components from one side, which is this, right, is equal to the acceleration of the center of mass in x, which is this, and then plus this. So that's alpha L over 2 cos theta. So let's write that down. We have the acceleration of a is equal to, let's make sure we copy everything correctly. So we have ACMX, so ACMX plus, and then we have alpha L over 2 cosine theta. It's alpha L over 2 cosine of theta. So the acceleration of a therefore becomes this, which we already know as minus g sine theta. So this is minus g sine theta. And then plus, now alpha, we know what alpha is in terms of the y acceleration. So let's first write alpha as this. So alpha is 2, so 2 ACM y over, let's make sure we write everything correctly, over L sine theta. So over L sine theta, and then this is L over 2 cos theta. Okay, we can cancel out the L's, we can cancel out the 2's, which will leave us with the fact that the acceleration of A is going to be minus g sine theta, and then plus, and then we have ACM y cosine theta, and it should just be sine theta on the bottom. And the only thing left to do is we just substitute this with what we found it to be equal to, which was this big expression. So the acceleration of the center of mass in y is going to be equal to minus g cos theta, so I guess I can just make this into a minus. So minus g cos theta times 3 sine squared of theta, so times 3 sine squared of theta over, and then we have 1 plus the same thing, so 1 plus 3 sine squared of theta, and then times cosine of theta over sine of theta. Okay, so we can simplify a couple of things. So we can cancel this sign with this sign, and we can actually put brackets around everything, and this is going to turn into a plus. So the acceleration of A will be equal to minus g sine theta times. So essentially I factorize g sine theta with g sine theta. So in the brackets I should have 1 plus, and then we've got 3. Remember the sine of theta just went out. So we have 3 cosine squared of theta over 1 plus 3 sine squared of theta, which can be simplified as minus g sine theta times, and this is going to be, so we bring this 1, we multiply top and bottom with this denominator, so this is going to be 1 plus 3 sine squared of theta, and then plus 3 cosine squared of theta over 1 plus 3 sine squared of theta. Sine squared of theta. And for this part, we're going to use the fundamental theorem of trigonometry. So this is just going to be 3. So we finally have that the acceleration of A is equal to minus g. And then we have 1 plus 3, that's 4. So it's 4 sine of theta over 1 plus 3 sine squared of theta. And that's the answer. Right? That's the answer, which depends only on the angle theta. And of course, it depends on g. So it doesn't depend on the mass of the rod, it does depend on the length. It only depends on theta. And remember, theta was this inclination of the channel with respect to the horizontal, right? So that is how you do this. Now, if you want to put numbers in, you can, because the question is asking us to find the acceleration for 30 degrees, for theta of 30 degrees. So this is minus g times, so it's 4 times 1/2 over 1 plus 3 times, so sine of theta is 1/2, sine squared is 1 over 4, right? So the acceleration is going to be equal to minus g times, and then we have 2 on top, and on the bottom we have just 7 over 4. So this is going to be equal to minus g times 8 over 7. And that's it. Now, the minus, remember, it tells us that the acceleration happens in the negative x direction, right? So our x direction goes up the slope or up the channel. And the fact that we have a minus, it tells us that the true acceleration of point A is down the channel, which makes sense, right? Because if you leave this rod alone, it will start sliding downwards, which is what you would expect, and hence you have a minus sign here. And that's the end of the question.